Alright, so the last video described the differences between this trans cyclohexane and this cis cyclohexane about the rate with which they would undergo an E2 reaction. And the take home was really that this one down here, because this tert-butyl group forced the chlorine to be in the equatorial position, it would have a rate of 0. It would not do an E2 reaction, while this one would undergo an E2 reaction. Now we're moving on to essentially how stereochemistry is not impacting rate as much as it is impacting the major product. So here we're again going to compare a cis cyclohexane versus a trans cyclohexane, and we'll see how that can impact the rate of the product of the reaction. So essentially we're doing the same thing. We need to find and make sure we have anti-periplanar carbon-hydrogen bonds. So if we convert this skeletal structure to a chair structure, we have a Cl that is up, so it's going to be axial in that position. And this is a CH3. It was supposed to be, now it looks like it's potentially bonding to that, but it is a CH3, and that CH3 would be in that position. So essentially, do we have an anti-periplanar hydrogen to that chlorine? So what does that look like? And the answer is yes. So we saw in the last video that essentially this hydrogen here is anti-periplanar to that chlorine. So is this hydrogen here. Both of them are anti-periplanar to the chlorine. And again, I'm going to draw the Newman projection here, but essentially that hydrogen is there. The CH3 on this front carbon is there. This carbon is right here. The leaving group chlorine is right there. A hydrogen is right here, and another carbon of the cyclohexane is right there. So we have an anti-periplanar arrangement of the hydrogen and that leaving group, and deprotonating this hydrogen here will allow us to form the alkene in that position. So looking at that mechanistically, let's draw those arrows. Essentially, the base is grabbing that proton. Those electrons are going down to kick out the chlorine. That produces the tri-substituted product. Do we have another anti-periplanar hydrogen? The answer is yes. We also indicated last video that that hydrogen is anti-periplanar to the chlorine. So we could have also grabbed the H in that position. So essentially the base could have instead have gone for that hydrogen, and that would produce a secondary product. It would have produced this product. So which of those is going to be the major product? Yep, you're right. The more substituted product. So that's the major product of this reaction. Because both of them are possible, and that's the more substituted product. And remember, the more substituted the alkene is, the more stable the alkene is. Now we're going to look at the other stereoisomer. All right, so we just looked at the cis starting material. Now we have the trans starting material. The Cl is going down, so we can put that Cl here on our cyclohexane. This methyl group is going up, so the CH3 is there. So this is a really stable molecule, right? We have two groups, they're both equatorial, that is ideal. But neither of them is a tert-butyl. Neither of them locks this into only equatorial. So essentially the double equatorial is available as a possibility. It's the major conformation but we are still going to see some of the other chair structure, the conformationally rotated chair structure. So essentially, as chair structures can rotate, this would do that. That would put this chlorine moving, like essentially that peak gets pushed down, it's rotated down. That puts the chlorine into this axial position. It puts the CH3 into this axial position, and there's the hydrogen right there. And essentially, now we have to say what hydrogens are antiperiplanar to this chlorine. So the hydrogens in the beta positions include this axial hydrogen, this equatorial hydrogen, this equatorial hydrogen, this axial CH3. I'm going to come back with the model of that right now. All right, so now I have the model of this. You can see that the CCl is going down axially. The CH3 is coming up axially. And what is antiperiplanar to this CCl bond? Well, if we look right down that bond, we see that this hydrogen here is antiperiplanar to that chlorine. What else might be antiperiplanar? Well, again, we can just kind of look over here. And the other thing that's antiperiplanar is, again, not a hydrogen, but is a CH3. Again, we have to remove hydrogens in these elimination reactions. So if a CH3 is antiperiplanar, it's not a reactive group. So what was antiperiplanar? This CH3 was antiperiplanar, and that hydrogen was antiperiplanar. So the only thing that can lead to a productive reaction is that hydrogen there. So essentially what happens is that base can only pull off that proton, so that's what it's going to do. Those electrons are going to come down, form a double bond there, chlorine leaves, and that produces, and I'll actually initially draw it as the chair structure. It produces a double bond there. So what's unique about this situation? Well, we talked about Zaitsev's rule about the more substituted alkene is the alkene that forms, but this breaks that rule because that is only possible if we have an antiperiplanar hydrogen. This is this structure as a planar skeletal structure species, and you see that the di-substituted alkene is the one that formed, not the tri-substituted. So the stereochemistry of the starting material has a really big impact on what product can form. We saw that the major product for this cis species was the tri-substituted alkene, but this trans species only forms the di-substituted, the less stable alkene, because of the stereochemical necessity for an antiperiplanar hydrogen. So again, this shows that the actual product that's made is impacted by the stereochemistry, and the example above was more about the rate of the reaction. This rate was really fast, while this one was a rate of 0. There was no product formation. So yeah, stereochemistry is really important in E2 reactions. It's a pretty challenging topic because we have to draw these chair structures, we have to draw Newman projections, but the more you practice it, the easier it's going to become. So build models. Yeah, models, man, you guys all have them. Use them, please. That's all I have to say about that. All right.